Good day, I'm Villapando,
And I am Abugni.
and now we will be learning about Kutta-Joukowsky theorem and the Coanda effect. So to better understand the Kutta-Joukowsky theorem, let us first discuss about the Coanda effect. So when you say Coanda effect, only remember two words, flow attachment. Coanda effect is an aspect that explains the phenomenon behind flow attachment of a fluid along a surface. It was first observed by Henry Coanda, a Romanian aircraft engineer on his aircraft in 1910. If that's the case, then what made his aircraft different that made him observe the soon-to-be Coanda effect? His aircraft was powered by four piston engines, but instead of driving a propeller, it turns an impeller at the front, which delivers air to the combustion chambers, wherein it would be mixed with fuel and ignited to create thrust. Technically, his aircraft is the first jet-powered aircraft. However, some sources claims that this never happened. Moving on, his aircraft was set to fly on December 16 of 1910. He expected that the exhaust gases responsible for thrust would disperse into the atmosphere. However, his aircraft eventually caught fire. He claimed that rather than dispersing, the exhaust gases followed the contour of the fuselage. It was not until 20 years later that he discussed the concept behind this incident by patenting a device for deflecting a stream of elastic fluid projected into an elastic fluid. An elastic fluid is simply a fluid with constant viscosity, such as air. He discussed his observation using three different scenarios, all using a discharge nozzle that produced a jet stream of air. In the first scenario, as the jet stream exits the nozzle, he notes that if the velocity of the jet stream is sufficient, it carries along a portion of a surrounding air like there's a suction effect, calling it the induced flow. In the second scenario, he noticed that the jet stream traveled upwards, but eventually followed the surface of the flap. He explained that the flap blocks the ambient air on the left that was supposed to be producing an induced flow just like on the right side, hence the unbalanced force. In the third scenario, he observed that the jet stream followed the curvature of the surface, similar to the second figure, in which he added that the highest point of the curvature creates a suction effect. So rather than allowing the air to go upwards, it forces the air to attach to the curvature until it travels to the opposite direction. So as a recap, Henry introduced the concept of suction in his patent devices that produces induced flow, wherein the jet stream carries a portion of the air and allows the jet stream to attach to the surface. Observing this, we need to ask, why does it happen? Well, the answer lies behind the concept of Bernoulli's equation. Bernoulli's equation explicitly states that the velocity and static pressure are inversely proportional to each other, which means the jet stream has lower pressure compared to the ambient pressure. And as we all know, pressure travels from higher concentration to lower concentration. This means that the induced flow is caused by, next, is caused by the pressure difference between the high pressure ambient air and the low pressure jet stream, as shown in the first figure. For the second and third figure, if all of the air near the surface is induced to the flow with no surrounding pressure to sustain it, this creates a vacuum or a pressure lower than the jet stream, meaning this forces the jet stream to travel on the surface while the higher pressure ambient air pushes it. Eventually, the jet pressure would be equalized with ambient pressure beyond the surface and soon be dispersed. An application of the Coanda effect are the high-lift devices of wings as it redirects the attached air from the lower surface to the upper surface through the use of slots. Next is a rubber ball being balanced overhead by a leaf blower. The ball is sustained in the middle as the jet stream travels evenly on all of its sides. If the ball manages to slip on one side, it would be pushed back to the middle by the momentum of particles. However, a common misconception of the Coanda effect is the water clinging to the spoon. This is a false example because the flowing water does not attach to the spoon due to, due to the higher ambient pressure, but it attaches due to surface tension, which then pulls the spoon and allows the water to travel on it. So again, Coanda effect is the attachment of a stream of fluid to a surface due to pressure difference with the ambient pressure being higher.
Moving on, Kutta-Joukowsky theorem is another attempt to explain the lift generation. So It is where it relates the lift and circulation of air. It is first studied by Frederick W. Lanchester in 1894, followed by Martin Wilhelm Kutta, and then by Nikolai Y. Joukowsky, each studied independently. This theorem will help us understand the reason behind the pressure difference of the upper and lower surface of a wing. We must also first visualize an airfoil with the presence of boundary layer, which results from the effect of surface friction and the viscosity of the fluid it travels through. Now we can briefly define circulation as the idea of a fluid circulating around an object, which according to the Kutta condition, displaces the stagnation point near the trailing edge of an airfoil. In this first cross-section of an airfoil, we can see two stagnation points, one at the leading edge and one at the upper surface trailing edge. At some time after the initial period, the stagnation point at the up part moves exactly at the trailing edge. Then the flow leaves the trailing edge smoothly. A starting vortex is formed downstream, rotating in a counterclockwise direction, which is an equal and opposite force of the clockwise circulation around the airfoil, maintaining the conservation of forces. This theorem can also be explained with the clockwise spinning cylinder perpendicular to the free stream flow direction. The upper part of the cylinder boosts the free stream's velocity just above it as it both moves towards the right. However, the lower part of the cylinder moves towards the left, which slows down the free stream velocity at this part, thus creating a static pressure difference above and below the cylinder, resulting to lift. As I have mentioned the Kutta condition, in summary, it states that for a given airfoil at a given angle of attack, the value of circulation around the airfoil is such that the flow leaves the trailing edge smoothly, just as shown in the first image. 2. If the trailing edge angle is finite, then the trailing edge is a stagnation point. Here we can see velocity 2 parallel to and coming from the lower trailing edge surface, and the velocity 1 parallel to and coming from the upper trailing edge surface. Meeting at the point 1 or trailing edge, these velocities are 0. Third, if the trailing edge is crossed, the velocities leaving the top and bottom surfaces at the trailing edge are finite and equal in magnitude and direction, leaving the trailing edge smoothly. To visualize the relationship of lift and circulation, we can observe these diagrams, where the arrow length represents the magnitude of airflow velocity. The first diagram shows the free flow around the wing, and the second shows the circulation around the wing. We can see the flow at the upper surface of these two diagrams goes to the same direction, but the flow at the lower surface will meet, thus the circulation will slow down the flow of the free stream in this lower part, resulting to the third diagram, which has a higher velocity, thus lower pressure at the upper surface, and a lower velocity or higher pressure at the lower surface, thus again resulting to lift. The theorem gives us an equation of lift as the product of air density, free stream velocity, circulation of air, and the wingspan. The Kutta condition must be met to be able to use this equation. So in conclusion, according to Anderson, the nature enforces the Kutta condition by means of friction. Therefore, in a way, we can't have lift without friction. To ensure that the airflow leaves the trailing edge smoothly, the viscous boundary layer must stay attached all the way to the trailing edge, and this boundary layer can't be formed without friction. Furthermore, we can conclude from this lift equation that denser air generates more lift, greater pressure difference will be achieved with faster free stream velocity, and the longer the wing, the higher aspect ratio, the lift increases. And that will be all about the Kutta-Joukowsky and Coanda effect. Thank you.